let me introduce our first speaker, so that's Andy Gordon. He works at Microsoft Research in Cambridge, but also has an appointment at University of Edinburgh, like the true Scot that he is. And so I'm a fan of his early work on applying process calculi, in particular to the specification and verification of crypto protocols. But he was also an early adopter and promoter of the probabilistic programming approach, and has relentlessly explored possible applications to spreadsheets in particular. So now he's going to share his thoughts on why statistical thinking is transforming programming language research. So thank you, Andy.
Thank you, Xavier. It's a great pleasure to be here at Collège de France. Thank you, Xavier, Jean-Baptiste, for the invitation. How to Lie with Statistics. This is a book that I loved when I was a kid, and it got me interested in the sort of tricksy things that people do with statistics and maybe some of the good practices we ought to follow. And I love this quote that's from the preface from H.G. Wells, the great science fiction author from about a century ago. Statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And I think that day has very much come. So statistical thinking is like the theme of my talk, and really the theme of the whole day. And tomorrow, as Xavier has been saying, that's really what probabilistic programming is about, using computers, using programming languages to empower people with statistical thinking. So my official title, Why Statistical Thinking is Transforming Programming Language Research. That's the main theme of my talk, but I am going to intersperse with a secondary theme about spreadsheets, as Xavier says. That's something I've been very interested in, how to bring probabilistic programming to spreadsheets. And so a secondary theme is why the dream of usable probabilistic programming in the spreadsheet is getting closer. So a bit about that. About, I don't know, 7-8 years ago, this is a paper we had that was at Popple, which is one of the main programming languages, perhaps there's probably no more prestigious, let's say, programming language venue than Popple, and it's organized by SIGPLAN, which is ACM's organization for programming languages, special interest group. And we had in the spreadsheet there a way of writing probabilistic models. So if I point, you can see, oh wait, let me start my timer, or else I will just go on and on with all this drama this morning. Okay, I know roughly when I started. Yes, so back then, we decided to take probabilistic programming to the spreadsheet, and we made up our own probabilistic notation here, which is sort of for writing, if you like, plates and gates notation, if you've come across that. But we had our own syntax for probabilistic formulas. Excel, or spreadsheets at the time, could only hold text in cells, so if we wanted to represent a probability distribution in a cell, we had to use strings. So we had a string like Gaussian 23.0 or 0.9 to represent distributions, which was kind of messy. And we had to have a specialist add-in to do inference. We couldn't use the engine itself. But still, it was a starting point. And since then, my mission really has been to empower more people to get more value from data. And the spreadsheet is a great place to do that because so many people have data in spreadsheets. So it's a great place to take machine learning and statistical thinking, which is what we were trying to do with tabular. So that was the dream. Now, let me come to today and talk a little bit about what we might envisage, how people would use probabilistic programming in the spreadsheet, at least in a very simple way. So this is a very simple example to show the kind of things that we might do. So imagine Clara. So this is a personal consumer situation. Clara wants to buy a sofa, and she thinks about her budget, and she builds a simple spreadsheet. And if you can see it here, she's got 2,000 euros income this month, for sure. Her rent is 1,100. Her commute is 85. The sofa she sees in the shop, bargain price 700 euros. But she's a bit uncertain about her utilities bill. And in spreadsheets, you can't really express that uncertainty. We actually did a user study, went and talked to 11 people about which aspects of the spreadsheets they'd built themselves had uncertainty in them. And we found several hundred occurrences of a cell that was uncertain. And in half of the cases, somebody had to put an estimate. So maybe they would put the midpoint but they couldn't express a range. So what Clara really wants to do is express this range between 50 and 150 euros, but she can't do that today in spreadsheets. The closest she could get is to use randomness. So she could write a formula that chooses a random number, which is what you see in the video. You saw it was drawing samples at random between 50 and 150. And so she can do that and then repeatedly recalc the spreadsheet. And then each time she'll get a balance where she subtracts the expenses from the income. And in this case, with that particular random choice, she's in credit, but sometimes she's not. And she can ask, am I above zero or not? So roughly speaking, for many years, the only way people could represent uncertainty like that would be to just mash, repeatedly recalc the spreadsheet to get samples. So we've made progress in the past few years, and this video shows exactly the same spreadsheet, except now we've captured this piece of grid as a bit of logic that we can do inference on, and we can actually, in this case, what we're doing is recalculating 1,000 times to get a sample from the distribution and then calculating the expectation. But the point here is that now we can hold an actual probability distribution in a cell as a record, and I'm showing it here. In fact, this is just in Excel today, it pops up this record, and you can see that it's got a pre-calculated expectation, it's got a particular number of trials in the sample, and it's got the actual sample itself as a nested array. So now we've got real programming language data structures, we've got a record containing an array that are sitting in cells, and now Clara can write a formula inside the spreadsheet that calculates her expectation, and it tells her that she's got a 3/4 chance of staying solvent, so she'll take a chance and she buys the sofa. So it's a happy ending for Clara. So that's where we are today, and showing where we can get to with some general enhancements we've made with Excel over these years. But to tell the story properly, let's start with the actual users. So spreadsheets got going commercially anyway with VisiCalc back in 1979. Dan Bricklin and Bob Frankston were the pioneers. Less well known is that the academic study of spreadsheets goes back to this researcher, Bonnie Nardi, who in the early 90s did ethnographies of how people were programming in spreadsheets. She went out and interviewed a whole bunch of users and asking them how they built spreadsheets. And she coined the term end-user programming, which was programming to achieve the result of a program primarily for personal rather than public use. So most of us, or most of our students, end up as professional programmers who write code for other people's use. Spreadsheet users are really different. They can be very expert in a particular domain and write really quite complicated spreadsheets, but they're not primarily interested in programming for its own sake, and they're really focused on code for their own use. But this is the really important class of programmers, and they're the ones that we're trying to reach when we work with spreadsheets and think about programming in the spreadsheet, and indeed probabilistic programming in the spreadsheet. Another study by Amy Coe, led by Amy Coe and others, just describe what these folks are like. They might be secretaries, accountants, children, teachers, interaction designers, scientists, or anyone else who finds themselves writing programs to support their hobbies. So that's end-user programmers. And then we really need to consider spreadsheets as being code. So this is Felina Hermans, another pioneer of the study of spreadsheets. And she's noting that ambitious spreadsheets may have thousands of formulas, sometimes developed over many years. Many of us enjoy the webcomic XKCD. And if you consult XKCD, they note that spreadsheets are far beyond the complexity of things like quicksort or self-driving cars or Google search backend. On the spectrum of complexity at the high end is the sprawling Excel spreadsheet built up over 20 years by a church group in Nebraska to coordinate their scheduling. So there's a real problem here. Felina's angle was to take ideas from software engineering and apply them to spreadsheets and to advocate tools for testing spreadsheets. And she found that end-user programmers already were writing tests in their spreadsheets. but she built other tools to find bugs in spreadsheets. On the programming language side, some colleagues of mine, Simon Peyton-Jones, dear colleague at Microsoft Research for many years, Alan Blackwell from Cambridge, Margaret Burnett, great professor of HCI from Oregon, wrote a paper about what is known as sheet-defined functions. And this was trying to introduce the idea of abstraction to end-user programmers, starting from the point that end-user programmers are comfortable writing examples of example calculations in the grid, and seeing if they could just use that as the way of defining a new function without extra special syntax. So here's an example where you have a calculation. So imagine the average isn't built into Excel, and you have an example of like 5 numbers here in a column from B3 to B7, and then you might count how many there are in that range with this formula, sum up the range with that formula, and then take the division to get the average. And so that's nice. This is typical in spreadsheets. You write a calculation like that, and it works just the once. So the idea of sheet-defined functions, or SDFs, is that you can nominate that the yellow is an input and the green is the output, and you have some UI to allow the user to say that. And then this introduces a new function, say called average, and then you can write a formula somewhere else that calls this sheet-defined function with some range. And the semantics is that when you evaluate a function call like that, you take the original bit of grid that defined the function, you make a fresh copy of it, you copy in exactly the numbers that have been passed into the yellow input, you recalculate, look at the answer that's in the green cell, and then you return it. So that's a simple idea of sheet-defined functions, and it goes back a long way. So about 5 years ago, a little bit after we had done the tabular system, I decided to join forces with Simon, because after waiting a long time, and it's a long story because they originally did the work in 2003, but by about 2016, the Excel team decided, let's see if we can take some of these ideas seriously, and started a big initiative called Project Yellow, which was to take programming language ideas and put them into Excel. And in particular, we wanted to remove the glass ceiling that limits what end-user programmers can do with Excel. So there are 2 main principles. One is to make Excel functions reflect the abstractions of our end users in the style of sheet-defined functions that I've just explained, but it also led to things like lambda that we've added, and also to make Excel's data values reflect the data types of our end user domains. And that's what I just showed you in the slide, or in the video earlier on. Remember, I had a record containing within it an array. So those are general concepts, records and arrays that can compose nicely. And you can use them now to represent concepts that are important for end users. So if you go to a hedge fund, you might find the hedge fund has a lot of data about some, some option they've placed. And that can very conveniently be held inside one of these compound structures in the grid. But for us as probabilistic programmers, it's great because we can hold probability distributions, as I showed, directly in the grid. So, as I say, I joined forces with Simon because this seemed the best way forward to bring probabilistic programming to Excel, was to actually make Project Yellow happen, and that's been a great experience. Fast forward, last year, for the second time, Excel made it into XKCD, and there was a comic strip, oh cool, Excel is adding a lambda function, so you can recursively define functions. So I was super proud. This has been the most prestigious thing that happened to work I've been part of, well, in fact, since this invitation to Collège de France. But that was awesome. It actually, as far as it's only the second time that Excel has ever appeared in XKCD, and as far as I know, it's the one and only time that a tech transfer from Microsoft Research has made it into XKCD. So that's fabulous. But how do you actually use them? So coming back to Clara and her sofa, and she's got uncertainty about how much it costs. It's somewhere between 50 and 150 euros. So we looked into the literature and discovered that a classic way to represent sort of end user uncertainty like that is to use a triangular distribution like this. This is taken from Wikipedia, where this is the density function of the triangular function, where you have a lower bound, an upper bound, and a midpoint. And so to represent this bit of grid I showed you earlier, we're calling range there. That function is not built into Excel. It's a lambda that we define with an equation like that. And it basically means make a call to the triangular distribution and sample between A and B with the midpoint being halfway between. And this is code that implements the triangular distribution. And this is just copied from Wikipedia. And you see it's using the Excel primitive rand, which just draws it uniformly between 0 and 1. So this is great. We can represent Clara's uncertainty using lambdas. I'll just point out that things like lambdas and the distribution and the records and so forth, those are actually now built into Excel. And what I show you here is what we call the Advanced Formula Environment, which is a project that's released by Microsoft and is owned by our research team. So it's not literally part of the product. It's a sort of beta part of the product. I'll have more to say about that later. And then sheet-defined functions, we actually have them implemented in the Advanced Formula Environment. And we take the bit of grid that defined Clara's budget, and in fact, we assumed it has no inputs, and its output is the 0 or 1 here, depending on whether the result is above 0. And our compiler, which is built into AFE, compiles to this lambda here, which if you squint at it, you'll see that it's basically making a copy of the grid with variables for, this is the let, and so we bind this variable E1 to 2000, D3 to 1100, and so forth. And so now we have a bit of code that we can call multiple times to sample in the simplest way possible from her budget, and hence we're able to calculate this distribution here. Inference, you can't see it now, but there's a function called sample that implements repeated sampling by calling this function, and it produces a distribution. And so all this is possible to do today. So please join us. So one call to action from this talk is that this code all runs today, and if researchers here, if anyone is interested in using our AFE, which is like a research vehicle for trying things out, like doing, for example, fancier inference, please talk to me. So this is the simplest thing possible. But you see, we can turn a grid into a bit of code, and so we can do all sorts of interesting things like that. Take its derivative, do much more efficient inference with it than simply Monte Carlo. So that's an opportunity. Let me just recap. So the dream of usable probabilistic programming in the spreadsheet. In some sense, it's been there all the time. People have been doing random draws in spreadsheets since the 80s. In fact, it's happened, in a way, probabilistic programming has been happening in the spreadsheet way before probabilistic programming languages. And there's various quite popular add-ins for doing it. What's new in what we've got now is you can do it within the formula language, which I think is pretty cool. You don't need fancy add-ins. And it's getting easier because of these general constructs like compound data, lambda, and SDFs. But now let me turn to the second part of my talk and talk about why statistical thinking is transforming programming language research. So I mentioned Amy Coe earlier. She had led that study of end-user programming that I quoted from, and she is a HCI researcher, has done a lot of work on spreadsheets and other kinds of programming, not just for end users. And she gave a great talk at Splash, which is one of the ACM conferences, one of the ACM SIGPLAN conferences, about 5 years ago, actually no, 6 years ago. And it was called The Human View of Programming Languages, and it really stuck in my mind. She quoted from Sherry Turkle and Seymour Papert. They had a paper called Epistemological Pluralism that was published in 1990. Actually, Xavier didn't mention it, but Xavier and I first met around about then, actually slightly earlier, when we were both interns at a company called DEC that some of you might remember. They had a great lab called the Systems Research Center, and we had a great summer together in '89. So just around about that time was when this paper was written. So it dates us a little bit. But they say equal access to even the most basic elements of computation requires this epistemological pluralism, accepting the validity of multiple ways of knowing and thinking. And this came from another ethnographic study they did of looking at how people were learning programming. And so Coe quotes them in this talk that I'm quoting from about a human view of programming languages. And she looked at a range of sort of ways of thinking about programming languages and the values they embody. So one of them would be programming languages is maths. And this gives you certainty. You get a true theorem, and you can gain enormous confidence that it's certainly true. And many, many discoveries are of that sort. Many, many papers at Popple, for example, have theorems as the main punchline of the paper. It's an interface, and so efficiency of how well it, maybe performance of the compiler is important in that case. Or another way of looking at it is its design, and then you may say, well, how usable, how much utility do you get from the design? Or it might be notation and so forth. But her general point, and I recommend you go listen to the talk, it's really cool, but her general point really is that there's an overemphasis on certainty. She says, when she looks at the way we spend time, most of our discoveries are about uncertainty, but there are a lot of values here that we don't explore all that deeply around design, notation, and media, and so forth. And about the same time, the SIG plan itself put together a great checklist, and this was against, they called it a preemptive strike against the replication crisis in computer science. And this is by luminaries, esteemed colleagues of mine that I'm listing here. And it's a really good piece of work. And in fact, it embodies statistical thinking about programming languages, for sure. I'm not saying we haven't thought about statistics before in programming languages, but it's very much about empirical evaluations using computers, like how efficient is an algorithm, how much space does it use, and so forth. And they've got a bunch of good principles here that they put out and form as a checklist. However, they say, because user studies are currently relatively infrequent in the papers we examined, we have not included them among the category examples. And I think this is such a shame, and this is kind of what Amy Cole is getting at, that in programming languages, we seem to have been really reluctant to accept the validity of studies based on talking to humans. And I've kind of come to this view by looking at spreadsheets, because as I've been explaining, spreadsheet users are not like us. They're writing code for themselves, and to understand them, you really need to go and talk to them. It's not like the classic sort of Xerox PARC way of operating, or DEC-CIRC, in fact, where we were. Their modus operandi back then was invent something for yourself and use it for yourself, and the world will follow and pick up on it. And the reality is that in spreadsheets, it's not like that. In a way, the system tabular that we built, I almost built this for myself to understand how probabilistic thinking worked. And mea culpa, I'm sort of saying other people don't do user studies. At this point in 2014, we had never done a user study. So we just put this up and thought it was cool, and we proved theorems about it, but we didn't really ask ourselves, is this actually usable? Is it helping Clara to make decisions? So in the last part of my talk, I'm going to talk a bit about a couple of user studies that we've worked on, and then I will conclude. So back to sheet-defined functions. And this is going to be an example of quantitative statistical thinking about a human user study in programming languages. And I should say, maybe I'll leave the anecdote about how hard this was to publish to later. So let me tell you about this. Elastic SDF. So remember the function I explained, how you can take this piece of grid and regard it as defining a new average function. Well, there's a problem, because remember I said the semantics of this is, if you make a function call to this grid, you will take your input, copy it into the yellow cells, recalculate, and then see what the answer is in the green cell. But what if you say average of x5 to x7, which has 3 rows? Well, you'll copy those rows in there and probably leave 4 and 6 on the naive understanding anyway, and get the wrong answer. And if you say average of a longer range, say G2 to G200, which will sort of go off the page, it's too big, and the calculations here will ignore everything below row 7. So this is a problem, I mean, a crucial problem, actually, with sheet-defined functions if they're actually to be usable, because obviously, it seems natural anyway that you'd want these to stretch, to be elastic. So that was the idea of elastic SDFs. So this is the user eye view that we wanted to deliver. The user writes an example with fixed size inputs using familiar copy-paste, like in Clara's example or in this one and many others. You very, very often have a table, maybe with multiple columns, and it's going to have variable numbers of rows. And magic happens, and I'm going to resist saying what the magic is here, because that basically is like 20 pages of maths, which I think is really cool, but today is not the day for it. But basically, in words, briefly, we sort of look at the fixed size model and we try and parameterize it so that it stretches. A bit like it's almost like a sort of polymorphic inference, problem that we add some size variables to the model and then see if it stretches, if all the different components of it would stretch suitably. But I'm not going to try and explain that here. And then the function works on input of arbitrary size. And this is great. And then we thought this automatically inferred elasticity will dramatically broaden the audience of folks who can use SDFs effectively. But this was now, I don't know, four years ago. And I'd seen Amy Coe's talk, and we were now working with HCI folks. We thought we really should do a user study. So I just want to tell you about that. This is something I wouldn't have done previously, but I think it was really helpful to do it. So what we wanted to test was whether this new mechanism was as good as the best alternative. And the best alternative would be something like map-reduce programming, what you might call combinator-based programming, where you have higher order functions, which would be enabled by lambda, that would let you express a computation that would work on arrays of arbitrary size. So we did a study, and I'll just explain the outlines of it. We had 20 participants. They were students mostly drawn from, some of them were students drawn from different subjects, and some of them had industry experience, and they had various professions. So these were like typical end-user programmers. The economist was always writing formulas to figure out their models. And then we had a procedure. I'm just going to outline it here. We made a video tutorial that covered sheet-defined functions and also this array programming. So we're trying to be fair to both ways of approaching this problem, because we expected that none of our participants were familiar with either of them. So we're trying to have a fair comparison of the two. So we made video tutorials, and then for each of the two approaches, we had a practice task that we would talk through with the users, and then we'd observe them as they try and did 3 other study tasks. And these were sort of typical calculations of, I don't have a slide about it, but it was calculations about expense reports and making them replicatable on different numbers of expenses. And so we got them to do those tasks, and then we administered a standard cognitive load questionnaire that was originally introduced by NASA, and it's a way of assessing, how much cognitive effort an activity has taken. It asks you questions to elucidate that, and it's a standard method. And then afterwards, we did a semi-structured interview where we just asked them questions about their experience and got some quotes about how they felt using the mechanism. And in brief, the findings are here, that there was a significantly lower cognitive workload using elastic SDFs than with SDFs based on MapReduce. So this was what we had been hoping for, and that's what we found. And we got some interesting quotes from the semi-structured interviews. I think elastic functions are easier to work with also with them, and they have the mental model that you have of Excel, because you can more than just follow your normal Excel workflow. And this, again, is the kind of thing we were hoping for, but actually finding users were experiencing that. We thought elastic SDFs are easier because they don't require you to go outside of your Excel workflow. You just more or less stay within it. And they also appreciated just the idea of being able to capture a bit of logic and reuse it, of not having to write the same things over and over again, and not having to persuade someone else to make a macro. So this is very typical, that the end user programmer is trying to perform a function like accounts or something, and that's their task that they're trying to get done. And it's a real pain if the need goes beyond their capability and they have to get someone else to come in. So that's actually validating sheet-defined functions, all up. Well, not validating, but it's a bit of evidence. Now, is this certainty? No, it's not, right? You don't get the certainty you get from a theorem, but it's some evidence. And it starts to guide you. You start to build up a sense of what people are actually wanting, which you don't get from proving theorems about elastic SDFs. it was, let me press on with a separate, let me press on. Something a little different. So reactions to Lambda in online forums. So this is a very recent piece of work we did. And this is not quantitative at all, but it's qualitative statistical thinking about data from users. So remember the advanced formula environment that I mentioned, and it's driven by Jack Williams in our team, who has built it and released it with the Excel team, and it's kind of promoted by the Excel team. This is it in action. And just starting up, and you can see it's got some boxes here for editing lambdas. And one of the cool things about working with the Excel team is that Excel gets a lot of publicity. And in fact, what I've noticed building up in the last 5 years is that there are influencers on YouTube who make videos about Excel. And in fact, just like anything else, like if you want to figure out how to, fix a puncture on your bike, you go to YouTube to get someone to explain it. The same is happening with Excel, and there are some influencers who have enormous followings. So Leila Garani, I think, has the most, 1.7 million subscribers, and she makes a lot of videos. And so the great thing for Jack is he didn't have to make this tutorial video because Leila did it for him, and she's really good at making videos. In fact, she's made a lot of videos about Lambda. So here's Leila talking about scan, which is a higher order function. This is her talking about recursive lambdas, which is really cool, explaining lambdas and more higher order functions by row and by call that make use of lambda. So the world is changing. I think this is really awesome. She is a really good educator. She is awesome. Her videos really get to the point and explain things carefully, and her explanation of lambdas and recursion is one of the best I've seen. I recommend you go watching it. So the world has changed. This is what higher order functional programming looks like in 2022. So back to our study, we thought that this is a new source of data about users. So we went out to these online forums like Hacker News, YouTube, which I just talked about, Microsoft Tech Community. Excel has its own blogs or places for people to add comments, and Reddit. And we got 2,700 comments that we actually looked at individually, and there were 4 of us on it. And I think every comment was looked at separately by at least 2 of us. And we used a method called thematic analysis, where we attached codes to the different comments. And some of them we just threw out because they didn't say anything interesting. So our purpose, sorry, I should stop. Our purpose here was to understand the perceptions of Lambda, because it came out last year, and XKCD talked about it, and we thought Lambda was cool, and we thought it's great for probabilistic programming, etc. But also, how do actual end-user programmers perceive it? And so this is a great way to get data on humans and how they felt about it. And so I won't go through all of this, but basically it was nuanced. Some people thought Lambda was great, and this is fantastic. Now we can do stuff we used to do in Scheme. Other people saying it's really bad because it's going to make spreadsheets unreadable. And there's a sentiment that many people express, which is that we like that the formula language is really simple, because it means if you take someone else's spreadsheet, you don't need to understand their macros, you don't need to understand their lambdas, you can just look at the standard syntax. So that's a point of view, and we weren't getting that otherwise. So that was really insightful for us. And there's a bunch of other points as well. So I recommend the paper, and it's just going to come out at VLHCC in a couple of months. Let me wrap up with 2 calls to action. Firstly, embrace the human in programming language research. I've been arguing that statistical thinking transforms programming language research, and I'm particularly thinking about human studies, data from humans, their comments, interviewing them, looking at how they perform in various kinds of tasks. And as I've explained, we get evidence. It's not certainty, but we can assess the effectiveness of new features and find patterns. And I consider yourselves to try using some human-centric methods. There's some great conferences. There's a Plateau workshop. There's an HCI PL summer school that happened last year and hopefully it will happen again. And there are many other researchers like Elena Glassman, Nadia Polikarpova, Sriram Krishnamurti, many others are doing great work applying user studies to programming languages. So I really advocate you go look at their papers. And another plea, if you review for PL venues, embrace a diversity of research disciplines. I'm going back to the many ways of thinking from Turkle and Papper and Amy Koh's talk. The paper on elastic SDFs, we did the gamut of SIGPlan conferences. We submitted to POPL and got rejected. We submitted to PLDI, we got rejected. We submitted to ICFP and got rejected. Eventually we submitted to JFP and got accepted, and it was the same work. Right? We weren't rejected because there was anything wrong, right? There was nothing, no bugs were found in the theorems, and there were no substantive criticisms of the user study. It was more like I had one reviewer actually say, "This is great, Andy," or "This is great, but you've only got in so many pages, and it's a bit squishy. If you chopped out the user study, you could explain the theorems better, and then we'd have accepted it." Yeah, that's just wrong. So please, if you're reviewing, embrace the diversity, and there are people who can review these papers like the ones I've mentioned. Second, final call to action, empower people with statistical thinking. I've spoken about the dream of usable probabilistic programming, and my call would be, come join us. We've got some great assets now if you would like to write code to do probabilistic programming in the spreadsheet, and we can make them available to you. So thank you for your attention.